The circuit consisting of pure resistance. We need to study in ideal cases. Practically, it may have some inductor, it may have some capacitor. There may be a combination of any of these, right? But theoretically, we study pure inductive circuit, pure capacitive circuit, and pure resistive circuit. Pure resistive circuit is possible that because of pure resistance, which is possible. That we also seen different elements which is having only the resistance, not the inductor and capacitor. Now, for example, what figure this you see, which is a simple incandescent bulb. That incandescent bulb will have a tungsten filament, the gas filled inside this tube, right? So when we give a supply 230 volt, this bulb produces an intensity, illumination, right? So this is a purely resistive load. The second, you can see the electric iron. For ironing clothes, we use electric iron. This is also working on purely resistive. This is also purely resistive circuit because this iron contains the heating element, which is particularly a nichrome wire, which is covered by some insulating material, right? So it produces heat, and we can use that heat for ironing clothes. The third thing that everyone is knowing, that this is bucket heater or electric heater, which heats the water in the bucket or in the heater itself, right? So this is also having a purely resistive circuit. It contains the same thing as there in the electric iron. There is a nichrome wire which produces a lot of heat, and that heat will be conducted inside the water, and water will get heated. So these are what the example of purely resistive circuit, purely resistive AC circuits. So we need to study the different properties for this purely resistive circuit. Now, how it can be in terms of the diagram, in terms of the circuit, what we have, the purely resistive AC supply, that it can be represented by this symbol, the circle, and inside that circle there is an alternate sinusoidal waveform symbol. And then the resistor which is connected across this source, the current start flowing, which is the small current I, instantaneous value of current I, and instantaneous value of voltage V. Let us see the voltage as a reference. So we can have V is equal to Vm sine omega, omega t. Voltage we are considering as a reference. So V is equal to Vm sine omega t. Right? Then the voltage across this resistance will be VR. We can connect a voltmeter, and which will measure the voltage across resistance. So let us see first the voltage and current equations. The voltage equation we already know because we have considered voltage source as a reference. So let us derive the equation for current. Now the instantaneous value for the voltage across the resistor is same as the source voltage. Why? Because in the circuit across this source there is only one element, that is resistance, which is connected across this source. All the voltage which produced by this AC source will be supplied to this resistance. So that's why this VR is equal to V, that is equal to this source voltage. Both of will be equal because of there is only two elements, there is a source and resistance. So all the voltage source will be supplied to this resistance. So VR is equal to V, and that is equal to Vm sine omega t. Right? Now apply Ohm's law to this instantaneous value of the current. Then I is equal to VR by R, because in the circuit only we have resistance, voltage source, and current. So we can apply Ohm's law. V is equal to IR. So I is equal to VR by R. VR by R or V by R, same thing. So we can put a value of VR, Vm sine omega t divided by R. Now we can write this in terms of the polar form, Vm at an angle of 0 degree and R at an angle of 0 degree. For resistance there is no term, so we can directly write angle 0. And for Vm, already the value of phi is 0, so Vm angle phi. Or we can have Vm by R, this is a value of maximum current Im. Let us see, Im is equal to Vm by R, then we have I is equal to Im angle 0. We can get the division for it. Vm by R angle 0 minus 0, it will be 0. So Vm by R angle 0. And Vm by R is nothing but Im, so we get this value. I is equal to Im angle phi. Or in terms of the equation, we can write I is equal to Im omega t. So the current through the resistive circuit and applied voltage are in phase with each other. What we are getting here, the angle is also 0. Omega t plus minus phi, the value of phi is 0. So what we see, we assume that the voltage is on the reference axis, and what we are getting the value of current, the equation of current, it is also from the same axis. So we can have both are starting on the same point. So this is the voltage and current. So from this equation, we can draw the waveform. See, for V is equal to Vm sin omega t, starting from the origin point, and from the same point, I is equal to Im sin omega t, which is starting. But only the thing is that the magnitude of current will be less than the voltage. So with respect to omega t. Now in terms of the phasor diagram, so we can draw the current and voltage both are in phase. So here the phase difference is 0, the angle phi is 0, right? And phasor represents with the RMS value of voltage and current respectively. So this is the phasor diagram and waveform. This we can draw with this voltage and current equations. I am not drawing by my own thinking. It is from the voltage and current equation. Both are having the same axis. There is no value of phi. Then both are starting from the 0. And the same phasor diagram we can have. Current and voltage are in phase. Then power in purely resistive AC circuit. So we know the basic equation of power, which is voltage into current. So let us calculate first the instantaneous power, which can be obtained by taking the product of voltage V and current I. So we have this P is equal to V into I. So we have the equation for V, Vm sin omega t, I is equal to Im sin omega t. Then take the product of this Vm into Im sin square omega t. Then let us we have sin square omega t is 1 minus cos 2 omega t by 2. So we can put it here, Vm Im by 2, 1 minus cos 2 omega t. Then separate these terms. So Vm Im by 2 and Vm minus Vm Im by 2 cos 2 omega t. Then above equation shows that the instantaneous power is made up of two terms. So this first term and the second term. We cannot simplify this term further. So keep as it is. So this is the instantaneous power for resistive AC circuit. But we can have the average power for it. There are two terms in this instantaneous power, Vm Im by 2. This is the constant part, because Vm Im both value will be constant and 2 is always constant. And the second part is what? The fluctuating part, because there is a cos 2 omega t. And due to this value, it will be fluctuating and has a frequency which is double of the frequency of voltage and current. Why double? Because 2 omega t. Omega t is the basic frequency, 2 omega t, which is the double of the frequency of voltage and current waves. Therefore, the average value of this constant term will be 0. Throughout the waveform, the average value will be 0. So when we put up the value of omega t is 0, we get the value which is 1. When we put 180 degree, then we'll get minus 1. When we put 360 degree, again we'll get 1. So the resultant, this value will be 0. For the second term, its value will be 0. So when we calculate the average power, then in the average of these both terms, the average of first term will be present, but the average of second term will be 0. Because as I stated that there is a cos 2 omega t, and the average of this cosine waveform or sine waveform is always 0 over a complete cycle. So we have average power is Vm Im by 2. We can have a simple arrangement, Vm by root 2 and Im by root 2. And we know what is Vm by root 2, which is the RMS value, and Im by root 2, which is the RMS value of current, RMS value of voltage and RMS value of current. So final equations, what we are getting, power P is equal to P average is equal to V RMS into I RMS in terms of the watt. So whenever in the circuit there is only a resistance, then power can be calculated by simply multiplying RMS value of voltage and current. So P average is equal to V into I. No one will ask you the instantaneous power equation, but the final power, which is what the average power, that V into I. So based on this equation, we can draw the power waveform. Now we have the voltage and current waveform. We already plotted it earlier. So this is Vm, V and I is waveform. Now look at that. Product of V into I, that the waveform is starting with respect to that, whose value will be greater than, because there is a product of V and I. So it will be increasing instantaneous power. Again it will be 0 when both the voltages are 0. We are taking simply multiplication V and I. Again in the second case, both are negative, so power will be positive. Negative becomes positive. So again the power will be in the same direction. This will be continuously. Average power, which is what the average of this instantaneous, so it is around this dotted line. P average is equal to V into I. So the impedance in purely resistive circuit, which is expressed as Z is equal to R plus Jx, as the reactive component is not present in the purely resistive circuit, so X will be equal to 0. So Z is only equal to R. So Z is equal to R, or in polar form we can represent R at an angle of 0 degree in terms of the ohm. So this is the impedance which can be represented over rectangular or in polar form. So Z is equal to R. Only resistive element is present in the circuit, so only R will be present. X term will be 0. Reactance will be 0. So remember this thing. So this is about purely resistive AC circuits. So we have the circuit diagram for it. Then we have voltage and current equations. Then based on voltage and current equation, we are able to draw the waveforms and phasor diagram by this voltage and current equation. Then instantaneous power we have derived, P is equal to V into I. Then by deriving instantaneous power, we can have average power. What we get the average power? V into I in terms of the watt. And by this equation of average and instantaneous power, we can draw the waveform for the power output in the purely resistive circuit. And the impedance in the circuit can be represented in the rectangular form as well as in the polar form.